Okay, can you hear me all right? Great. So this is an unusual audience, I'm told. The public lecture would have people from the community, generally interested, students, whatnot, but there are a lot of black belt physicists in the audience. Can you raise your hand if you're a professional physicist? Okay, good. So everybody look around. So what is special about this lecture is when you are lost or confused by something, you could turn to probably somebody on your right or left who's a professional physicist, and they can clear up the situation, clear up whichever mistakes I made, and then you'd be better prepared for the test at the end. So please go ahead and do that. Okay. Anyway, it's my pleasure to be here at the University of Washington. Thank you for inviting me. And I'm going to tell you the story of how observations of exploding stars called supernovae showed to us that the universe is not only expanding, that we knew for a long time since Hubble, but rather accelerating, expanding faster and faster due to a mysterious and unexpected component of the universe called dark energy. But before I get to the exciting stuff, I want to give you sort of a crash course in cosmology and how we understand the universe. So let's cover the prerequisites now, okay? This is a deep image of the universe. This is actually the deepest image of the universe ever taken, at least up till about last week. This was taken with the Hubble Space Telescope, its advanced camera, by picking a blank area in the sky and keeping the shutter open for 3 or 4 weeks. As anybody who has done photography knows, the way you observe very faint light is to keep the shutter open a long time. And so in this picture, you could see tens of thousands of galaxies, the faintest of which are 1 trillion times fainter than what you could see with your naked eye. And this is just a tiny patch of the sky. If you took a single grain of sand and you held it out at arm's length, you would cover a patch this size. So this is just a trivial portion of the universe by comparison. Now, when you look at a picture like this, the universe looks static. What I mean to say is, you know, you keep the shutter open for many weeks and nothing looks blurry, nothing looks like it's whizzing around, and so that would be your reasonable guess. However, this is a false impression. In reality, the universe acts like it received a big kick that we call the Big Bang, and now the separation between galaxies is growing. You can think of the universe like a giant loaf of raisin bread rising in the oven. The galaxies are like raisins, and they are all moving apart from each other. The ones that are further apart from each other move apart faster because there's more space or more dough between us and some of the more distant ones. So you might wonder, how do we know that our universe is expanding? And the answer, of course, is we checked. And we've actually checked all the results in this talk, so don't worry, I'm not making things. But seriously, how would you determine that? How would you? Well, judging from that animation that I showed you, you need to be able to make some basic measurements of the objects we see around us. You need to be able to measure how far away things are and how fast they're moving. So let's cover the first one. How far away are things? How do we measure distances to objects? Here on Earth, we have lots of techniques for doing this, and so let me remind you of those because that will help us as we go further. If you want to measure something relatively nearby, you might use this technique called parallax. You see a crew of surveyors. They want to measure the distance to that tree, but they don't want to swim across that stream. So they cite the position of that tree relative to a distant mountain, and then they move their equipment along something called a baseline, measure the new angle, and with the baseline and the angle, they've completed a triangle, and they can measure the distance using simple geometry. We often don't have a baseline large enough in the universe to do this as much as we would like. Another method that we use is the method of lighthouses. So everybody's familiar with this. A ship captain at night wants to make sure he or she is far from the shore, and so they look for a lighthouse, which is they know to be very luminous, to actually look very faint, which tells them that they are very far away. However, they could be fooled. Let's say it was a foggy night. Then the lighthouse might look faint even as they're about to crash on the rocky shore. Then we have a very similar concept to the lighthouse, except instead of a powerful light, it's a powerful sound, and the attenuation, or hearing a quiet sound, tells you that you're far away, allows you to judge distances. Another method that we use is what I call objects of known size. This is sort of what we do every day. We look out and we see things we recognize, they just look small, and so that tells us they're far away. Or in the case of this squadron of airplanes, we assume these are the same kinds of airplanes, just those small ones are in the background. It could have been the case that those small ones are like baby airplanes and that they're all together, but we understand that that's not how airplanes are built. And so these are the techniques we use to figure out how far away things are. So what we use in space is a little similar and a little different. We have to use telescopes, and we have to use what nature provides, because most of these objects in some ways are kind of human-made creations. So one of our favorite methods is that method of lighthouses in a very special way. And that is when a galaxy, like the one you see over there, might have 100 billion stars in it. When one of those stars explodes in an event called a supernova, happens about once a century, then that supernova can act as what astronomers call a standard candle. A standard candle is any object whose luminosity you understand well, so that you can tell when it's far away how far away it is from how bright it appears. So when one of these goes off, it was just a single star. I didn't quite catch the sound from that, so I don't know if we're having a sound issue or not. Hopefully we'll cover that. Sound? Check. Okay. But anyway, so the supernova fades away, and we can measure its distance from its brightness using what's called the inverse square law, that the brightness falls off as 1 over the distance squared. So if it's twice as far away, it's going to look 4 times as faint. If it's 3 times as far away, it's going to look 9 times as faint. So finding these supernova explosions is one way we can measure distances in the universe. The other quantity, if you remember from that animation that I showed you of the expanding universe, is you want to measure not only how far away things are, but how fast they appear to be rushing away from us. How do we do that? Well, in this case, we look not at the brightness of the light of a distant object, but we look at the color of the light of a distant object. So a supernova, like this one, may emit light at some color, presumably, let's say, a relatively blue color, and then because of the expansion of space, as that light propagates to our telescope, the wavelengths of light are stretched by the expansion of space, so that what is received is longer wavelength light. Longer wavelength light is redder light, so we call this phenomenon the redshift, and it would look more or less like this. Here's a standard candle. It's emitting light. The light is blue, but through the expansion of space, by the time it's received, it's much redder. This might remind you of something else you learned about in high school, the Doppler shift, where objects moving, like an ambulance or something that is also emitting some periodic phenomenon like sound, has its wavelengths stretched as well. But there's an important distinction here. In the case of the Doppler shift, it's individual objects moving this way and that way in no particular pattern. In the case of the universe, it's seeing everything around us with a redshift, and a redshift that is greater when objects are further away, that tells us that the universe is actually expanding. So going back to the animation that I showed before, we can now get quantitative about this. We can now go out with our telescopes and we can measure the distances and the redshifts or velocities of some of these galaxies, and seeing a linear relationship, measuring a linear relationship between these two is the signature of an expanding universe. That's what tells us the universe is expanding, because it says it's because something is further away that it is moving faster away from us. And we can measure then the expansion rate of the universe as the slope of this line. So if the universe were expanding faster, does anybody hear an echo? Is it just in my head? Okay, no echo in the back? Good. Okay. So if the universe were expanding faster, we would see a much steeper slope. If it were expanding slower, we would see a shallow slope. If the universe was contracting instead of expanding, we would actually see a negative slope, which is not what we see. And so this is how we measure the expansion rate of the universe. To measure this slope a number that's called the Hubble constant. Okay, so this is not just a thought experiment. This was actually measured for the first time by the astronomer Edwin Hubble back in the 1920s using the 100-inch telescope, which he's sitting at there, to, oops, excuse me, let me back up one, measuring distances by some of the methods that I described and combining that with a measurement of the redshifts of those galaxies that had been measured by Vesto-Slipher a decade earlier. He made this really iconic graph. This just, you know, I know it only looks like probably like the physics experiment you did in high school that didn't go so well, but this is actually an extremely important, the first indication that the universe is expanding is the relationship between these two. I often tell my students that I don't have a tattoo, but if I got a tattoo, I would probably get it of this. That's to me how iconic it really is. So this is a terribly important graph. And then with additional observations, so in my graduate work, I extended this work using supernova explosions, measuring further out. And so Hubble's original measurements would fit in this tiny little red box in the lower left-hand corner. But as you go further and further out, you see the same thing. The universe is expanding. Okay, so now that we've gotten our first sort of cosmology lesson, we can immediately learn interesting things about the universe, things that I thought when I was a kid that you learned from, you know, a philosopher or a clergy member, and that is, when did the universe begin? Okay, and the reason is because of the power of mathematics. We can imagine the universe expanding as time goes forward at the rate that we have observed, that we've learned how to make measurements of distances and redshifts, and we've learned this Hubble constant, the rate at which the universe expands. So by mathematics, we can run this movie backwards in time. So imagine now we're running a movie of the universe backwards in time, and now the universe is contracting instead of expanding at that rate. And we just keep running the movie backwards in time until everything is on top of everything else. That's the point which we call the Big Bang, when everything starts. That we could call the age of the universe. And to first order, to a simple mathematical approximation, that number is about 1 over the value of the Hubble constant, assuming that nothing has changed dramatically over the history of the universe, that it's more or less expanded at that rate. Okay, so in the 1920s, when Hubble made the first attempt to measure this expansion rate of the universe, he got a very large number that implied its inverse, a very small number, meaning that the universe was very young, only about 2 billion years old. Now, even in 1929, we knew that that was wrong. We knew that the Earth was older than that by geological dating. However, it turns out that measuring the Hubble constant, the expansion rate of the universe, has been very hard. There's been almost a 100-year quest to do this. And the reason it's hard is because it's difficult, as I described, to measure distances to great precision. So this was a recent article a few years ago in the New York Times that showed the sort of 100-year history of measuring Hubble's constant. So the numbers used to be very high, leading to very young ages. And over time, we learned very important things about the universe that refined our measurements. We learned that there have been 2 generations of stars, and we had to know which we were looking at when we were making measurements. We began to use digital detectors to make measurements instead of photographic plates. We launched the Hubble Space Telescope, largely dedicated to this project. We learned how to measure distances with supernovae, and particularly in the last 30 years or so, the measurements have really started to narrow down to a specific value. And I gave a more technical talk earlier today about the best efforts today to measure the expansion rate of the universe using the Hubble Space Telescope that come in around 73 plus or minus 1, implying a 13 billion-year-old universe. So that's a relief. We are no longer concerned about the universe and the objects in it being older than the universe itself. Okay, so that's great. The universe is expanding. We have that down. We can measure how fast and some basic things about it. But the question you really might have, as many cosmologists and philosophers about, is what happens then? What is the fate of an expanding universe? Okay, it's very much like the question Isaac Newton asked: what is the fate of a cannonball when it is fired from a cannon on a mountain on the surface of the Earth? And there are different scenarios that are possible. It really depends on how fast you fire that cannonball and how massive the Earth is, or the gravitational pull on the cannonball. So if you fire it with a very little velocity, okay, or if it's a very massive planet, surely that cannonball is going to fall down to Earth. not go very far. If you fire it with a greater velocity, or the mass of the body is very small, it will certainly travel further. Eventually, if you give it enough velocity, it will escape the gravitational pull of the Earth, what we call escape velocity. Or likewise, at a given velocity, if the mass is very, very small, that will surely happen as well. So this analogy is actually quite a good analogy for the universe as we thought of it by the 1990s, which is we knew the universe was expanding, like the cannonball being fired, but we didn't know how massive the universe was and whether its own self-gravity would cause the expansion to stop. And so we wish to measure that aspect. Now, that's how we thought about it in the 1990s, but Einstein, who thought about it decades earlier, had a very different idea of what might be going on. Einstein talked to the best astronomers of his day in 1916 and asked them what the universe was doing. And he was told incorrectly that the universe was static, that it was not expanding and it was not contracting. And he was confused by this because he knew that if you took a collection of matter like this and it was static and you let go, whoever was holding on to it let go, the attractive gravity of that stuff would cause it to start to fall together. Now, Einstein had been misled because astronomers of the day didn't know about the universe. They thought the Milky Way was the universe, and of course the Milky Way is pretty static. However, he struggled with this condition, and he actually made an amazing discovery. He made a discovery that in his theory of gravity, while the gravity of matter in the universe is attractive, the gravity of empty space itself could be repulsive, something he called the cosmological constant, or today we would call dark energy. And he imagined that these two flavors of gravity, the attractive gravity from stuff and the repulsive gravity from space, must be in some kind of perfect balance. This is the only thing that would explain what the astronomers were seeing, that the universe is static. However, that story changed quite a bit some 10 years later when Einstein learned from Hubble, as Hubble and others learned that there were galaxies outside the Milky Way, and those galaxies were moving away from us, and that the universe was expanding. He famously came to visit Hubble at Mount Wilson in 1931 to check out this story, to make sure he found it really convincing. I love this picture on the left here because I think this must be some kind of public relations shot, because you know, at the time, astronomers were not using their eyeballs to measure things. They were using photographic plates because the things were very dim, and so you'd have to add up light for hours on a photographic plate. So if Einstein is checking out Hubble's observations, he cannot see anything with his eye. And it would have been very unusual for Hubble to have a pipe at the around these photographic plates anyway. So as I said, this must be a PR shot. But nevertheless, Einstein came away from the visit convinced that Hubble had measured that the universe was expanding, and hence his idea of balancing these two kinds of gravity was unnecessary. He called it a blunder, famously, or anecdotally. Okay, so that's fine, but then today, how can we measure if our cannonball, our universe, is slowing in its expansion enough to fall back to Earth, or in this case, recollapse, or whether it would expand forever, right? If it were like, you know, the stock market, this looks like our stock market, actually. If it were like the stock market, you know, you would just wait quarter by quarter and see how it goes. But the universe changes very slowly. So instead of looking forward in time for things to change, we use a certain trick of the universe, which is to recognize that already all the information we get about the universe is delayed. That is, the universe doesn't instant message us. All the information we get has a built-in delay that's sort of like the distance light has to travel over the speed of light. And since the distances are very great, even at the speed of light, this is quite a delay. So when we look at some distant standard candle, it's not telling us how fast the universe is expanding now. It's actually telling us about how fast it was expanding 1 billion years ago. And when we look at a more distant one, it's telling us how fast the universe was expanding 2 billion years ago, and so on. So what initially seems like an annoying aspect of the universe, that we just can't get undelayed information, actually turns out to be a powerful tool, that we can still see the past trajectory, the past expansion history. We can see how that cannonball was traveling and if it was slowing down enough to stop or not. So by the 1990s, most cosmologists thought the right answer, our universe, was represented by the model either on the left or on the right. On the left is a very heavyweight universe. In our parlance, omega, or omega matter, the key term for how heavy the universe is, would be greater than 1, in which case the expansion going on now would be slowing. It would be decelerating a lot. So much so that it would stop in the future, the universe would start contracting, and then in a big crunch. Or the universe was relatively lightweight, that omega was less than 1, in which case the universe had escape velocity, like that cannonball. It would continue to travel out forever. And astronomers thought by the mid-1990s, if they could observe supernova explosions very, very far away, they can look at the past trajectory of the universe and, in essence, weigh the universe by this amount of deceleration and figure out which of these was the likely scenario. Now, it turns out not any kind of supernova explosion will do. There's a very special class of exploding stars that are called Type 1a supernovae, but they come after an idea from the Indian astrophysicist Chandrasekhar, who showed in the 1930s that a certain kind of star, a white dwarf star, could only be stable up to a certain critical mass. That mass is called the Chandrasekhar limit. It's about 1.4 times the mass of our sun. If that star becomes more massive than that, you'll get a runaway thermonuclear explosion. And so what we believe goes on in nature is those kinds of stars exist below the Chandrasekhar mass, but sometimes they live near another star, and mass might be pulled over to the other star by gravity, and when it attains the Chandrasekhar limit, it explodes. This sounds like a perfect standard candle for cosmology, right? You get something that always blows up at the same mass. It's like nature's standard bomb. And they can be seen halfway across the universe, and they're as bright as 4 billion suns. That also makes them a great standard candle. Not only are they incredibly homogeneous, but they're visible halfway across the universe. So in my doctoral thesis in the mid-1990s, I began to work on measuring and using these Type 1a supernovae to measure distances. And here are 4 that I measured in my thesis in 1995. People often ask, how do you find these supernovae? And usually it's the bright spot at the end of the arrow that you see in the pictures. But I don't know. No, actually we add the arrows to the pictures afterwards. You actually do have to find the supernovae, and they're pretty rare. There's only about 1 in a galaxy like ours per century. And so in order to find them, you need to look at a lot of galaxies and be very patient, you would imagine. So instead of 1 per supernova per 100 years, right, you could actually stare at 100 galaxies, and over a year, you're bound to find one. That still doesn't sound like great odds, but you can do even better, right? You can look at 10,000 galaxies at a time. I showed you those images from Hubble. We can fit 10,000 galaxies in a frame, and then you're bound to find 10 supernovae in a year. The basic idea here is finding a supernova is sort of like winning the lottery. It's a really rare event unless you buy all the lottery tickets. And so that is more or less what astronomers learned to do in the mid-1990s, was to take wide field images and find supernovae by this way. And then the other key element was the development of computer algorithms that were really good at sifting for these supernovae by essentially matching the qualities and the parameters of 2 sets of observations. So you take a set of observations with your telescope, you wait 30 days, you take another set of observations, you digitally match them, subtract them. Computers are good at telling you there's a new point of light there, and by this method, 2 teams of astronomers and physicists went out to find some of these distant supernovae. So I was on the high Z supernova team that started in 1994 to, we thought, measure the cosmic deceleration of the universe, thinking that that's what we would do and it would tell us about the ultimate fate of the universe. These are my colleagues who worked on this from 1994 till the late 1990s. Now, come mid-1997, I was fortunate, I was a postdoc at the time, and I was picked to lead the first analysis of a large sample of supernovae. And so I began that work with the guidance of a very simple relationship, this very simple mathematical relationship that's true, that the amount of deceleration of the expansion just depends on what the mass is of the universe divided by 2. Anybody can divide by 2. That part isn't the hard part. And ignoring or negating Einstein's idea. I mean, if it was a blunder, why should we stick it in the equation, okay? So that was pretty straightforward. And then I began analyzing the data, and the supernovae would tell you how much deceleration there was, and you would then associate that with the mass of the universe. So I wrote a simple computer program to do that for our data. And you know, computers don't really know physics. And so if you give them a simple equation and it's not the right equation, you know, they'll make it work and they might tell you something nonsensical, which is what I saw. So as I was analyzing the data, I wrote the program to tell me, okay, what is the answer? What is the mass density that explains the deceleration? Not yet realizing that I had the sign wrong. The universe is not decelerating, it was accelerating. And so by forcing this equation on the data, it reported that the mass of the universe was not just below 1, that was one possibility, or just above 1. Instead, I got back a negative number. Now, that doesn't make any sense. There's no such thing as negative mass, but computers don't know that. They just know that you gave them a very simple equation, and the thing on the left-hand side came out negative, so then the thing on the right-hand side better be negative too. I hadn't yet realized that the universe was accelerating, and what you actually need is something else. The matter in the universe will only slow the expansion. You need something like Einstein's idea, what gives rise to repulsive gravity, to have a chance to change the left-hand side of the equation and cause the universe to accelerate. So after a few days of looking at this, I recognized that Einstein's cosmological constant was likely necessary, introduced it into the calculations, found fairly high confidence that it was a necessary component, and then began to talk to my colleagues. And it's very interesting to look at the chain of conversation in a scientific collaboration when they see something surprising. So I'm going to take you through that now. So this is early 1998. Alex Filipenko, who's a well-known professor in Berkeley, many of you probably know him, I was working with, kicked it off with an email. Adam showed me fantastic plots before he left for his wedding. Our data imply a non-zero cosmological constant. Who knows, this might be the right answer. Bruno Leibengut in Germany, our colleague there, concerning a cosmological constant, I'd like to ask Adam or anybody else in the group if they feel prepared enough to defend the answer. There is no point in writing an article if we are not very sure we are getting the right answer. So there's a kind of understandable conservatism amongst collaborations of not, wanting to look foolish and getting things wrong. Brian Schmidt in Australia, who led the team for finding the supernovae. I agree our data imply a cosmological constant, but how confident are we in this result? I find it very perplexing. My thesis advisor, Bob Kirshner, known to many, was on sabbatical in Santa Barbara, and he wrote, "I am worried." In your heart, you know the cosmological constant is wrong, though your head tells you that you don't care and you're just reporting the observations. It would be silly to say we must have a non-zero cosmological constant only to retract it next year. So it's definitely very, very concerned about that. Mark Phillips in Chile, as serious and responsible scientists, we all know that it is far too early to be reaching firm conclusions about the value of the cosmological constant. So we're kind of going back and forth here. John Tonry in Hawaii, who remembers the detection of the magnetic monopole and other gaffes? On the other hand, we should not be shy about getting our results out. So, in the history of physics, there's long-standing memories, corporate memories of all kinds of famous non-discoveries or things. And so, those always come out to haunt physicists when they think about new discoveries. Alex Filipenko, if we're wrong in the end, then so be it. At least we ran in the race. What's he talking about, the race? There was another competing group at the Lawrence Berkeley National Laboratory led by Saul Perlmutter, who they were doing a very similar experiment. They had their own data set, and we were kind of in a race with them in the sense that we were competing for time on the same telescopes. We couldn't always both get the time, and so we were both looking to demonstrate that we were making good progress. And so if there was something to discover, neither team wanted to not be involved in it. I wrote in Berkeley, coming back from my wedding, packing my bag for my honeymoon. The results are very surprising, shocking even. I've avoided telling anyone about them because I wanted to do some cross-checks. I wanted to get further into writing the results up. The data require a non-zero cosmological constant. Approach these results not with your head or your heart or head, but with your eyes. We are observers, after all. Alejandro Clociani in Chile, if Einstein made a mistake with the cosmological constant, why couldn't we? That always seemed, it was like certain mistakes, if you make them in good company, maybe that's okay, I don't know. Nick Sunsef in Chile, I really encourage you, Adam, to work your butt off on this. We need to be careful. If you're really sure that the cosmological constant is not zero, my God, get it out. I mean this seriously, you probably never will have another scientific result that is more exciting come your way in your lifetime. And, you know, Nick was exactly right. And, you know, it's great in a collaboration when you have a range of people with a range of experiences, because then you sort of have that memory of those things. So we said, okay, let's go ahead. And so we put out this paper saying, based on observations of supernovae, the universe expansion was accelerating, and that about 70% would be in the form of the cosmological constant or dark energy. This was our discovery paper, and the team at Lawrence Berkeley Lab came to the same conclusion at about the same time. And so this was very exciting to the community. This became the breakthrough of the year in 1998, that presumably even Einstein would have been amazed that this thing that he had, you know, come up with and then discarded was back and was actually the dominant thing right now in the universe. Okay, so what is really going on, though? Why is the universe accelerating? I mentioned the idea of dark energy, but what does that mean? Okay, well, we have a few different ideas or options of what could be going on, and sort of in this order are sort of priorities. Okay, the first is vacuum energy, or the cosmological constant, what I mentioned. Einstein didn't have a specific microphysics description of it, but today we would basically say, well, you know, quantum theory demands that there is some background energy, some zero-point energy, some energy in empty space. It's almost unavoidable. And then, in general relativity, that kind of energy will give rise to repulsive gravity. So that sounds like our candidate, right? Except there's a terrible quantitative mismatch between the quantum idea and what we actually observe, so that these are almost, you know, word-level ideas that just don't integrate well because we don't have a quantum theory of gravity. And so it's tempting, but it's not fully fleshed out. Although we think something like this happens, I mean, even the Higgs field is a form of dark energy. It's not our dark energy, but it is, because it's energy everywhere. Option two would be dynamical dark energy. So this would be a field in space. You could think of any field, the magnetic field, the electric field. This would be the energy of a field, its potential energy, that could temporarily act or mimic a cosmological constant, except the difference is it might dissipate over time, or it might grow from non-existence. A third possibility is a modification of gravity, that over long ranges we have broken Einstein's theory of general relativity, and so what we are seeing is somehow artifacts of that process. However, going back to around the year 1998 or 2000, we were less concerned about these issues than we were of just checking, are we sure that we're getting the right answer? Could something be fooling us? Earlier in the talk, I discussed how you could be looking at a lighthouse and get fooled if it was a foggy night. What if we were looking at supernovae? They looked faint. We thought that meant they were far away, but likewise, there was some kind of cosmic fog in the universe that was throwing things off. The idea here being that when we looked out at a distant supernova, we thought faint meant it's far away, and hence there's dark energy. But what if faint meant some mysterious kind of dust or fog in the universe that makes things look faint? There's really no dark energy. And theorists were writing papers like this, suggesting, you know, nobody had ever seen intergalactic, what they called intergalactic gray dust before. But on the other hand, nobody had seen dark energy before. So, you know, you couldn't just assume that this wasn't going on. And so we recognized at some point that we needed to look for ever more distant supernovae, because if you look through a longer and longer path in the universe, through more and more of this gray fog, you will keep seeing this dimming effect. Whereas if what we were seeing was the effect of dark energy has only been dominant or important in the last 5 billion years or so. When the universe was younger and more compact, it would not have felt the presence of dark energy, and you'd get a very different result than over here. And so the idea was to go out and look for more distant supernovae to discriminate between these two possibilities. Now, to say something about a more powerful telescope, I need to briefly remind you about the history of telescopes in space. Telescopes are, the heart of what we do for observations, and they've gotten better ever since Galileo. So this is improvement in sensitivity over the eye since the time of Galileo, as astronomers have built bigger and bigger telescopes, moved them to mountaintops, got digital detectors that were superior to the eye or photographic plates, put them up in space like the Hubble Space Telescope, which for this particular field allows us to resolve or separate the light of a supernova from its host galaxy compared to what you see from the ground. Then sometimes astronauts go up to the telescope and they replace the instruments that are there with better instruments. So we now have almost that trillion factor of improvement over the eye. And I note to self, I need to add for the new James Webb Space Telescope yet another factor of about 100 improvement over the Hubble Space Telescope. So more powerful telescopes has been incredibly great. And so in the early 2000s, we used new instruments on Hubble that the astronauts put up there in order to find these very distant supernova explosions, ones that exploded when the universe was less than half its present age. Here again, the arrows are back. You could see where the individual supernovae are in the before and after pictures. And so what this showed us was that supernovae were telling the truth. There was no gray dust or gray fog. Instead, we live in a really interesting universe, one that is not slowing because of the dominance of matter in the universe, but actually was early on, but is now speeding up due to the dominant presence of dark energy, with the universe now expanding about 20% faster than it was just 5 billion years ago. Of course, in cosmology, we're very careful, we are very conservative. It's not enough that one method or technique shows us something. Supernovae were the first in 1998 to show us that the universe was filled with dark energy, but then there were many other lines of evidence, like the many methods I showed you of measuring distances. We have other techniques. There's a technique called the integrated Sachs-Wolf effect, which just means that there are bundles of light coming from the early universe that fall into the potential wells of clusters of galaxies. That means that they gain energy when they fall in, and then they lose that energy when they climb back out. But dark energy has the effect of increasing the size of the clusters and weakening the amount of energy that goes in. And this effect has been seen quite strongly. Another test is that the cosmic microwave background can be used to measure the geometry of the universe, which tells us the total amount of energy in the universe. And when you take that total amount and you subtract off just the amount due to matter in the universe, you get a leftover 0.7 that is the same as we see here for dark energy, is the same as these folks see. Two others that I'll mention is the largest clusters of galaxies that exist have been unsuccessful at pulling in new galaxies because the effect of dark energy, which pushes those back out. And we've seen a change in the absolute scale of the universe from the time of the Big Bang to the present that requires a boost due to the presence of dark energy. But the way I ultimately became convinced that dark energy was real and that the universe was accelerating was when we won the Nobel Prize in physics, because, that's the Swedes never get this wrong. And so the two teams shared the Nobel Prize in Stockholm in 2011, and this was very fun, something you never expect to happen. However, there was a dark side, really, to all this merriment, which was illustrated in this episode of Big Bang Theory, if you've ever seen that show, when they were apparently watching us collect our Nobel Prize and, making fun of us, really. Here, let me play that for you. Right, so it's exactly what Sheldon said, that, we had managed to win the biggest prize in physics without any more understanding of the quantum underpinnings of gravity than God gave a goose. Exactly correct, that the universe is accelerating, but we don't really understand at a deep level why. So that's sort of where things stand now, is we have some ideas of what's going on, but we don't have a really detailed understanding. And yet still the investigations go on, because without that lack of deep understanding, there is still the possibility that we are not really on the right road, or we are partially on the right road. And so in recent years, there are additional puzzles which have developed. One, the thing I've been working on the last 10 or 15 years is another curiosity, which goes by the name of the Hubble constant tension, or could be seen as a new clue. So in our present understanding of the universe, then, over the last 13 billion years, we went through a period where the universe was dominated by dark matter and the expansion was slowing down, as you see here. This is expansion rate of the universe. It was slowing down, and then eventually it started to pick up and is now accelerating. And the expansion rate of the universe today is what it is after these episodes, okay? And that's measured locally, and the Big Bang was back here. However, there are other observations now from the cosmic microwave background. You probably heard about these, from particularly the Planck satellite, that tells us the exact same story, the same road: dark matter in the beginning, decelerating expansion, dark energy dominated, acceleration at the present. However, it's a parallel story. It's the same qualitative model or description, except with somewhat different values, so that the value of the expansion rate you predict today is somewhat smaller by about 9 or 10%. And the uncertainties on these things have gotten so small that these disagree at quite a significant level. And what is curious about this is, in order to connect these two, what the Big Bang says the expansion rate should be and what we actually observe it to be, requires us to understand really at a deeper level this cosmological model. This is the model we have today, which we call lambda CDM, or vanilla lambda CDM. This is how the universe would have looked shortly after the Big Bang, when it was mostly atoms, photons, neutrinos, and dark matter. And here's how it would look today, where it's mostly dark energy and dark matter. In order to make this prediction, we have to take very simple guesses about the nature of this. Maybe those guesses are too simple and are causing some discrepancy here. Maybe they still have something to tell us about the nature of the universe. We certainly know that without addressing or understanding this discrepancy, it's hard to say how old the universe is, because one of these roads brings you back to a younger universe than the other one does by about 1 billion years. And so this is part of the present moment. So whether you're consider the current situation good or bad, whether it's you're an optimist or pessimist. If you're an optimist, you say, hey, this is pretty good. In the last 20 years, cosmologists have come to understand the nature of the universe, what it is composed of. We have names for everything. We have percentages for most of those things. However, there is large uncertainty about the specifics, the microphysics of about 95% of this. If you're a little more pessimistic or concerned, there are some funny business going on right now. For example, how fast the universe appears to expand seems to depend on which end of the universe you start looking at, from the beginning or from the end. And so this could be evidence of still something left in for us to learn about the universe, or about the nature of dark matter and dark energy. Some of my colleagues have ideas these days what could explain this: some kind of new dark energy, a kind of new light particle like a neutrino, another episode of dark energy. It's clear that more data is needed. We are left with a story which has large incomplete areas, like the first time you survey the globe and you have these continents that are dark. You don't know what's inside them. You know, we have these areas that are not well understood, and we have some anomalies. And so short of new theoretical insight, new data is needed. But new data is coming. There are new space telescopes which have been designed to study dark energy in particular. The European Space Agency is building one called Euclid. NASA is building one who's called WFIRST. It's recently been renamed Roman. And there are ground-based telescopes like the Rubin Observatory, which people here work on, that have the possibility of addressing these questions, which of those three options are most likely, by measuring whether the dark energy is constant, whether it's been changing over time, or whether any description fails, that is, whether we have broken general relativity. So that is an exciting moment. Another exciting moment you might have heard about in the last couple weeks is we also have a new telescope for the Hubble Space Telescope called the James Webb Space Telescope, which launched about 6 months ago, and we just saw through pictures just a couple weeks ago that everything has gone splendidly. This is a telescope which is much bigger in size than Hubble. It lives much further away than Hubble at a point called Lagrange point 2, which is 4 times the Earth-Moon distance. It runs much colder than Hubble, where there's a sun shield that keeps light from the Earth and the sun blocked, so it sits in its own shade, where it can get down, some of the instruments down to 5 or 6 degrees Kelvin. So the telescope itself then is very quiet and doesn't emit, and so you can see very distant objects. And if you look at some of the first pictures that have come out, they're breathtaking. This is a deep image taken comparing Hubble, which is the first image you see, to what the James Webb Space Telescope sees. And I could look at zoom-ins of this all day. The amount of additional resolution, the detail, the sensitivity, and keep in mind, this is just a 2-hour exposure on the James Webb Space Telescope. I was showing you Hubble's deep fields have taken 3 or 4 weeks. Imagine if we spend 3 or 4 weeks with this new telescope staring at one spot. Imagine how, what kinds of distant objects we will see, how far. It's almost a paradigm change to me, where with the previous telescope, things are mostly dark with spots of light, and this is getting so good, it's almost more spots of light with some spots of dark, meaning, you know, light is starting to become more common. The old paradox about the sky being dark at night may not be totally true, because the sky looks relatively bright. So I will end here with telling you, why is it that we study dark energy? It sounds so esoteric. Why is it so important? Well, first of all, it's most of the universe. Until we understand it, it's hard to say we really understand most of the universe. It's intricately linked to the fate of the universe, the origin of the universe, our ability to tell the whole history of the universe. But I think really why particularly physicists are most excited about it is understanding dark energy lies at the nexus of sort of 2 areas of physics that currently are incompatible. Atomic or quantum level physics, the physics of microscopic space, and the physics of macroscopic space, gravity, general relativity. So we don't know how to unify those 2 things. People have worked on that, but nature knows how to do it, and so by watching how nature does it, by studying dark energy, we hope to learn more about that process and solve some of the biggest riddles in the universe. So I will end there. Thank you very much for your time.
Thank you so much, Adam, for this great lecture, educational and entertaining. We can take questions now. We have 2 microphones. Yes? Oh, just 1 second, please. We have 2 microphones at the bottom of the auditorium here, left and right. So you can, if you have a question, you can come downstairs and line up and ask your questions.
No physicists allowed, by the way. Just kidding.
George Burbage and Margaret Burbage wrote a book on quasi-stellar objects.
Sorry, George Burbage.
And Margaret, his wife.
Right.
Or you can say it the way,
So
husband of Margaret. Yeah, the Burbages. They wrote a book on quasi-stellar objects that nowadays we call quasars.
Okay.
He was asked in 2001 at a seminar kind of like this, focused on the big problems and all that, what he thinks the big problem is. And he says, oh, it's my observations from 1960 whatever of the distribution in redshift of these quasars. He says, yeah, they peaked when star formation peaked. Everyone knows that. But there's little ripples with the periodicity of a certain amount that he calculated with a Fourier transform, and he believed, but no one in the audience did. I wonder if type 1a supernovas, if you look at the redshift distribution, show any kind of ripples. A big peak at 1.
We don't see any ripples or periodicity in the distribution. We see a rise and fall over time that is essentially tied to, there was a point in time when star formation in the universe peaked at high redshift, and type 1a supernovae are white dwarf stars, which are old stars, after stars are formed that take a while to produce. And so what we see is the type 1a supernova rate looks like the star formation rate delayed by about 1 billion years because it takes 1 billion years to produce these white dwarfs. We don't see any ripples, periodicity, hieroglyphics or anything like that.
So what's your favorite hypothesis about what dark energy is and why?
What's my favorite hypothesis about dark energy? Certainly that it's either a cosmological constant or dynamical dark energy is, seems the most likely. But, I still wouldn't rule out that there's something we don't understand about gravity and that something plays a role in how we think of dark energy. So I think all the options have merit, and I wouldn't dismiss any of them as not possible. I think we have it about right in a rank-ordered list of most likely, but I don't know. We're fortunate that we have a number of experiments that are going to be going on in the next few years that really have a decent shot at answering this.
I was going to ask about the possibility of some of these supernova being from binary white dwarf mergers rather than single white dwarfs, because the white dwarf binary rate over redshift and the white dwarf single supernova rate over redshift is probably different.
Right.
So would that cause some sort of systematic effect if you weren't able to tell between them?
Yeah, it's a good question. So something we don't totally understand about type 1a supernovae is whether these are two white dwarfs which merge into each other, or whether it's one white dwarf and one normalish star where mass is transferred over. In a way, it's kind of immaterial to the cosmology because we don't know the answer to that question, and we don't model the supernovae using either model or story. Everything we do is completely empirical, treating them as standard candles, looking for additional information to standardize them, and the key information is the rate at which the explosion decays or fades. So the ones that fade very fast are the fainter ones to begin with. The ones that fade slowly are the brighter ones. And so if we learn the answer to the first question, what the progenitors are, it wouldn't inform or change the way we do cosmology because it's based on this empirical information, although I would very much like to know the answer to the first part, the progenitors.
I think there are questions over there.
There's another
Hello?
micro? Yeah.
Yeah, I was just wondering, if you have a personal suspicion about the discrepancy between the Planck values? Is there a particular explanation you favor right now? Or
Is there an explanation I favor? Certainly new physics is tempting. When you have two really good measurements and the only thing you can't do is connect them with a model, and that model was phenomenological and vague, right? Your first thought is maybe there's more physics in the model that we don't understand. So, that is certainly my going in bet. But then, when I look at my colleagues actually try to change the model in a way that fits this, it's challenging, it's difficult, the data's quite good. So I'm looking forward to, again, new data sets coming over the next few years that can shed light on this by testing some of the possibilities. But I think it's a real puzzle. It's certainly one of the most interesting puzzles I've ever seen. It's an interesting problem, it's interdisciplinary, it connects measurements in the low redshift universe to the high redshift universe. I didn't mention there's a sister or twin tension called the sigma 8 tension, which looks very similar, where you start at the early universe, the cosmic microwave background, use the cosmological model to predict how clumpy the universe should be today, and the universe is substantially smoother as observed than it was expected to be. Reminds me very much of the Hubble tension. The universe is expanding faster and it's smoother than it was expected to be. My gut feeling is that these things are related somehow, which again gets me to new physics because the measurements are totally different, but we don't yet know what that is. Sure.
Can you talk more about the future observation strategies that you're going to be using and your colleagues will be using to approach this discrepancy?
Sure.
You mentioned JWST and Euclid
Right.
and WFIRST,
Right.
but is there anything fundamentally different in how you're approaching these problems? Or is
Yeah.
it just going to be a function of statistical number gathering of
Well,
various
first of all, I would
segments?
say these problems are well enough known that it's not just me who's going to be making these measurements, but all my colleagues who have access to all kinds of facilities and have different angles at doing this. So anything from the cosmic microwave background, let's say stage 4, and on like that is critical because some of the ideas of what solved the Hubble tension are other particles or other episodes of dark energy which leave imprints or signatures in the cosmic microwave background. So some people will pursue a CMB solution or clues. We will use the James Webb Space Telescope to improve the resolution of the observations of, let's say, Cepheid variables, or to reduce the impacts of dust. Instead of observing in the near infrared, we'll observe even further to the near infrared to reduce that even more. Other colleagues will use Roman and Rubin observatories in Euclid to better characterize the recent expansion history of the universe and see, is there any element there that could help solve the tension? Like if dark energy was not a cosmological constant, but it was some kind of scalar field dark energy, that could play a role in explaining this Hubble tension. So there are lots of possibilities, but now they spread out over the whole map. LIGO, which is gravitational wave experiment, has its own method for measuring distances using the technique called standard sirens, where you actually use the event itself to, in spiraling neutron stars, to tell you what the luminosity in gravitational waves is, and then you observe the gravitational wave signature, and you can measure a distance that way. So it's completely parallel to what we do with light that you do with gravity waves, but it's obviously independent. So all of these could be the next shoe that drops, you know, the next thing that goes, oh, that points in a direction, that confirms this part, or it leaves more room, wiggle room in some other part.
Yeah. Could you please talk a little more about the difference or the similarity between the formation of the dark matters and the formation of the atoms or the elements we already know? Thank you.
Can I say more about the formation of dark matter and the formation of atoms?
Yeah.
I can't say very much about them. I mean, just that they both form in the early universe in the first, 10 to the minus 34 seconds, and that they, the proportions in which they form comes out of certain theories, and for the most part, we don't observe that early in the universe any of the kinds of things I've talked about. So, yeah, I guess I'm not sure what else you're looking for.
Thank you.
Okay.
Hi, so I have two questions. One is, have you ever met Chandrasekhar?
Sorry?
Have you ever met Chandrasekhar?
No. He died in 1995, and I guess I was in graduate school then.
Yeah, his sister was my teacher in middle school.
Wow.
Yeah, for 3 years.
That's great.
So my physics question, is there a relationship between inflation and the dark energy expansion you're seeing here?
Right. Yes and no. I mean, yes, in that they invoke similar physics, this repulsive gravity feature that's in general relativity. No, in that we don't think there's any natural connection between them, that they're different energy scales and they have no relation. Yes, again, in that I have colleagues who've tried to think of deep theories about how they are connected, and some people have claimed that there could be connections. So I would say it's not, at face value, it doesn't seem like it. Sort of way out theories suggest it could be, and at a very deep level, yes, they're connected by the use of repulsive gravity and general relativity, which is this phenomenon that is, it's exotic, but it's a part of GR.
And is the first 3 seconds of the universe, was that inflation or was that something else?
Yeah, even before the first 3 seconds is inflation. By 3 seconds, it's just regular expansion.
Right. Thank you.
Sure.
Hi. So you talked a little about dynamic dark energy, and
I talked about what?
Dynamic dark energy.
Dynamic dark energy, yeah.
And
Quintessence.
So, to my understanding, this is basically like, instead of it being homogeneous, it's like the energy density can change at different points in space. And so I was wondering if that's true, then what is driving that change? Because doesn't that change itself take energy?
I'm sorry, I still didn't quite get the question.
Yeah, sorry. So am I correct in saying that like the energy density is shifting in space? It's different at different points.
It's shifting in time. It can also be shifting in space as well.
So if it's shifting in time, then isn't there another energy source that's driving that shifting?
Well, it's a changing in the energy from kinetic energy to potential energy. So a field can be rolling or moving, then it has kinetic energy, but it also has potential energy as well. And so it's the potential energy which is the thing that causes the acceleration or what we see. And so there's a transformation going on between the two.
What's driving the transformation?
I guess the rolling. I mean, I guess the fact that there must be some kind of dynamical friction.
So we'll eventually stop rolling?
Maybe. I'm not sure. I mean, I think it depends on the particular quintessence model or story you have. Some get coupled to other things, so they could be trackers. They could track something else. They can have interactions. In which case, it depends what else is going on there.
Thank you.
Sure.
So I'm wondering if the acceleration of the expansion has anything to do with, or has any implications with regard to the Big Bang, because the Big Bang is you're running the clock backwards and you reach a singularity. Is it possible if you've got, instead of a straight line of all the matter converging at time 0, if you've got acceleration or deceleration happening, could you have a asymptotic solution at eventually, instead of a convergence or in a singularity, or could you have a divergence, or what does it imply?
The only real connection I know to the Big Bang and acceleration is probably more that the best theories suggest that the cosmological constant we get that gives rise to acceleration may be kind of a basic variable that's selected in some way when the universe starts. And in fact, there have been many theories going back that the cosmological constant we have is the size it is because it's anthropically set. It is a size that allows us to exist, that allows complex structures to form through gravity. In fact, Steve Weinberg wrote a paper many years ago presumably kind of predicting the value of the cosmological constant based on this argument that there could be many universes, and we have to have a value that's likely, but the most likely that still allows life to form. So that's the only connection I know.
But does it introduce any uncertainty into the existence of a singularity as you run the clock backwards?
I don't think so.
Hi there, rare non-physicist here with a basic question. How do you tell that a certain supernova is type 1a? Because otherwise, you don't have a base.
Yeah, that's a great question. So a type 1a supernova is the explosion of a white dwarf star, which at that point in its life is mostly composed of carbon and oxygen. And so in the explosion, you will see the products that result from thermonuclear burning of carbon and oxygen, which includes some unburnt carbon and oxygen, as well as silicon, which is a natural product of fusing carbon and oxygen, sulfur as well, and certain iron peak elements. So you could say it's sort of like, how do you know whether you burnt a log or something else? And it's like, well, I'll see certain ashes made of certain materials. So we will see ashes, and the spectrum shows us they have sulfur, silicon, iron, a certain signature, whereas the other main supernova type, which is called a core collapse supernova, has different elements. Usually we'll have hydrogen or helium, which is not present in a type 1a supernova. So it's different composition of the ashes.
Okay. Thank you. And is the expansion constant in every direction? Is it just a constant, or is it a function of space in any way?
Well, it's probably not constant in time, but we think it's relatively constant in space.
Okay. Thank you.
So, I'm a high school student, so this might be like a pretty simple question. I was wondering, in the early universe, was an over here. Oh, sorry. Okay. I was saying I am a high school student, so this might be a silly question, but why did the concentration of like dark energy lower dark matter lower, and then dark energy is like prevalent now, 75%, but earlier on in the universe it was mostly dark matter. Like,
right.
What is the change in why?
What's the change in why? Because when I give those proportions, that's the density in those things. And so when the universe is more compact, if there's a fixed amount of matter, the density in matter becomes greater. Right. Dark energy is constant in space as far as we can tell. It has a density that doesn't really change. So if you have one thing running the movie backwards that's becoming more concentrated, and the other thing that's staying fixed, then over time, the thing that gets more concentrated will dominate.
So of course, in the future, it'll lower even more, right? As the
Correct. So in the future, dark matter is diluting. Matter is diluting as space expands.
Okay, but where's the extra energy coming from if the density stays the same, but the volume of the universe is expanding?
Where's the energy of what?
Like dark energy, you said the density is staying the same, right? But the volume of the universe is expanding.
Right. There's more dark energy.
But where is it coming from? If the density is the same,
right,
but the volume is expanding.
So are you concerned about whether energy is conserved in the expanding universe? This is kind of a complicated question. It depends on what, we only ever promise you that energy is conserved in a closed system. So what is exactly a closed system in what may be an infinite universe is unclear. And then we also have to keep careful track of the different types of energy. So there's energy in the curvature of space, there's energy in radiation, we're losing energy in radiation, we're gaining energy in dark energy. So you have to do a careful job of keeping track of all the energies, what a closed system is, but my more theoretically minded colleagues tell me it's still conserved. So,
thank you.
And I believe them.
I have a question. A lot of the analysis in your very interesting talk about analysis of the universe expansion is based on the presumption that the universe expands, and that, of course, is based on the data which you presented. Which
yeah, I mean, it's an observation that the universe expands.
But also the fact that the Big Bang origins is at our galaxy, Milky Way.
Yeah,
which
that's
makes
not true.
That's not true. Okay,
So,
so I was going to ask, is there
there
something that points
well,
to the other
as I said, I
origins
know
of
it's
the
a
Big
poor analogy, but think of this infinite loaf of raisin bread, right? Pick any raisin that you're sitting on, look at the other raisins. They are all moving away from you, right? Whichever raisin you're sitting on. So the phenomenon of seeing everything redshifting around you is independent of where the center is. There is no center of an infinite loaf of raisin bread. And so, there's no center required. It's just that everything is expanding. Does that help?
Yes.
Okay.
Thank you.
Okay, we'll take one more question.
Hi, basically my entire physics experience has been taking the class AP Physics, so I'm probably one of the most qualified people here. But so you mentioned earlier that there were two teams competing over trying to get that information, how you were like scheduling conflicting appointments with telescopes. Like, why is this field so competitive? What do you project this used to be, like the information to be used for? Do you think?
Sorry, I got half your question.
Oh, yeah, sorry. So why do you think this field is so competitive? Is it just because people want to make a name for themselves, or do you think this, do you project there to be any specific use for this information other than just understanding?
Why? Let's see. You're asking why would two groups compete to make measurements? Is that right? How do I answer that? Once there is more than one group, there's another group, right? Because they, people think this is an interesting problem, right? So they both go up to the telescope committee, and it's very oversubscribed, these telescopes. So one group says, can we have the time we want to do this experiment? The other group says, can we have the time we want to do this experiment? And there's not enough telescope time to do all possible experiments. So the telescope committee says, we'll pick one of these, but we'll make the data available after a year to all groups so they can analyze it. And so that is generally what is done. However, the group that formally gets the time gets funding as well to actually do the experiment. The group that looks at the data later, they can do that in their leisure, but they can't do that. So I guess it's inherent in the system that, that people are hired to do the job. I guess that's a competitive process because there's more than one group that wants to be hired. It's interesting, it's exciting to people. They want to be involved in it and do it.
But do people expect there to be any specific use from this information that they want to acquire, I guess?
Curiosity.
Just curiosity.
Knowledge, deeper understanding of the laws of physics.
So what you're saying is that as a 6-year-old child, I had all the qualities I needed?
Yes.
Okay.
Yeah, most people who are physicists that I know are interested in the universe and are curious people. And this is not an enterprise that will lead to the iPhone 26, but it may lead to a deeper understanding that leads to, I don't know, the iPhone 226 or something. I mean, the GPS that's in our iPhone is not something that if you had asked Einstein what he was working on, he would have said the GPS for phones, but without the better laws of physics, we don't get that kind of technology.
All right, thank you.
Let's thank our speaker again, guys. Thank you. Thank you very much. Before we leave tonight, I would like to inform you of two upcoming events. First is that the next Frontier of Physics lecture will be on November 8th by Art MacDonald, who got the Nobel Prize in Physics in 2015. We very much hope you can join us here. But also, if you cannot, the lecture will be live streamed from the Department of Physics website. And the second is much sooner, tomorrow night, as part of the the SNOMAS summer study. We have what we call Physics Slam, where 4 young physicists will compete with each other on who would give the most entertaining explanation of some of the most exciting issues in physics today. So if you want to be entertained by physics, come back tomorrow night. Thank you all very much. Have a good night.